Hello, welcome again. We are covering the topic centrifugal compressor for civil services main IFS and Gate Aerospace exam. And in this next subtopic is non-dimensional quantities for plotting compressor characteristics. So we'll plot the compressor characteristics, but first we'll study the non-dimensional quantities required for plotting compressor characteristics. Why non-dimensional quantities? Because if we go on drawing the compressor characteristics by delivery pressure versus mass flow rate for a fixed rotational speed, okay, or delivery temperature versus mass flow rate for a fixed rotational speed, then these quantities pressure and temperature depends upon so many variables like inlet pressure, inlet temperature, so and type of working fluid. Then number of variables becomes very huge. Okay. So to draw this characteristic, so then it will be impossible to take into account the variation of each and every variable. Suppose intake pressure changes, then delivery pressure changes, and subsequently suppose temperature changes, then again delivery pressure changes. So these variations will be huge. So it will be impossible to draw all these variations. So instead of this, we will choose pressure ratio like delivery pressure by intake pressure. Now we have combined two variables in a single variable, delivery pressure and intake pressure, two variables. If we take delivery pressure by intake pressure, then it will be one variable. If we take delivery temperature by intake temperature, then it is a single variable. But if we take delivery temperature and intake temperature, then there are two variables. So by the dimensionless technique, we are reducing number of variables. Okay. So by and by doing this, we will draw only two sets of characteristics, okay, to represent compressor characteristics. So I will read this out. The performance of a compressor may be specified by the curves of delivery pressure and temperature plotted against mass flow for fixed value of rotational speed. Okay. But these characteristics, however, are dependent upon other variables such as conditions of pressure and temperature at the entry to compressor and the physical property of the working fluid. Okay. Next point, any attempt to allow for full variation of all these quantities over the working range would involve an excessive number of experiments and make a concise presentation of results impossible. So taking all the variations of pressure and inlet intake pressure and intake temperature and different speed will require excessive number of experiments. Okay. And then it will be possible to draw these characteristics. Okay. Much of this complication may be limited by using the technique of dimensional analysis, by which the variable involved may be combined to form a smaller and more manageable number of dimensions. Okay. So we, instead of delivery pressure, we choose pressure ratio, delivery pressure to intake pressure. Instead of temperature, delivery temperature, we will use temperature ratio. Okay. Then the number of dimensionless number of group is reduced, number of variables are reduced. So as will be shown, a complete characteristic of any particular compressor may be specified by only two sets of curves. If we do this, we can draw the curve for performance curve for compressor by only two sets of curves. So before going to these curves, first we will reduce the number of variables also. How? Suppose temperature is one of the variables. Okay. So if we multiply it by R, then it will become RT. Okay. And for an ideal gas and in compressor is ideal gas, P is equal to rho RT. So RT will be equal to P by rho, and dimension of P is ML minus P minus T, and dimension of rho is ML minus T. Okay. So fundamental variables are now only three, M, L and T, and the dimension of RT will come out in terms of fundamental variable is L square by L square T minus T. because dimension of P by rho is L square T minus 2. Okay, so dimension of RT would be same as that of P by rho. So if we take separate dimension for temperature, then the fundamental variable will be 4, but now we are reducing number of fundamental variables by using this. Okay. So reading this out, when considering a dimension of temperature, it is convenient always to associate it with the gas constant R, so that the combined variable RT being equal to P by rho has dimension ml minus 1 T minus 2 divided by ml minus 3 is equal to L square T minus 2. Thus they are the same as those of velocity scale, because this is velocity scale dimension. When the same gas, uh, for example, air is being used during the testing and subsequent use of compressor, R is finally eliminated, because R is same, because gas is same. But if the different gas is used, then R has to be taken into account. Okay, so this is about RT. So next point is, if we take P with RT, then P by RT is your 2. Okay, so if we are taking the variation of P by RT, then we can eliminate the variation of rho. But rho is an important property in case of compressor. But if we take P with RT, then we can eliminate the influence of rho. So that is your B point. A physical property of the gas which undoubtedly influences the behavior of the compressor is density, but if the pressure and RT product are also cited, its inclusion is superfluous, because P by RT is density. Okay. Now next point is viscosity. Third point, or the property of the working fluid is, main property of the working fluid is viscosity. And for this we take the Reynolds number. But in case of compressor, the flow is highly turbulent, so we can neglect the influence of viscosity. So this is the third point or 3 point. A further physical property of gas which in theory would also influence the problem would be its viscosity. The presence of this variable would ultimately result in emergence of dimensionless group, that is Reynolds number, having the character of Reynolds number. In a highly turbulent condition which generally prevail in machines of this type, it is found from experience that influence of this group is negligibly small over the normal operating range, and it is customary to exclude it from turbo machinery analysis. Okay. So now these are the main points. During these points we can say that diameter of impeller, speed of impeller will drive the non-dimensional thing. Mass P01, inlet stagnation pressure, P02 outlet stagnation pressure, RT01, that is having the units of velocity scale, and RT02 are the 7 variables, 1, 2, 3, 4, 5, 6 and 7 variables. Okay. Now we will drive dimensionless group from these variables. Okay. So bearing the above points in mind, it is now possible. It is now possible to consider various quantities. So by doing this, we are taking 2 variables here. Okay, or we will drive dimensionless group to eliminate the variation of each and every variable here. Okay. That will do in next.